start the recording now and stop sharing and let Alex take it away. Alex has also shared his slides with me, so I'll post them in the chat so people can follow the slides while they're listening to the talk as well.
Okay, so shall I start? Can everyone see my slides?
Yep.
Yeah. Okay, so I think I should start. Right, so I'm talking about sort of the computational complexity of finding normal surfaces. So this is all stuff that I did with my supervisor, Ben. So this, I guess this work started during my honors project. So, I mean, maybe the thing I should say is that means probably that everything should be understandable if all you have is like a sort of undergraduate level of background. So hopefully it shouldn't be too difficult. The other thing is I think there are a few people here who might have seen me talk about some of this stuff before. So hopefully, I mean, there's also some details that I haven't talked about before. So hopefully it won't be completely like old stuff. Okay, so let's actually start. So I'm going to start with a motivating example, which is the problem of unknot recognition. So a knot is just, I mean, it's just an embedding of a closed loop in the 3-sphere, or if you don't know what the 3-sphere is, just think of R3. So just in 3-dimensional space, you have a closed loop. And somehow the question is it possible to untangle this loop? So let's actually sort of formalize this. So we say that two knots are equivalent if you can continuously deform one knot into the other without passing the knot through itself. So like, if you have two strands, you're not allowed to sort of push one strand through because otherwise then everything is trivially possible to untangle. So what's a trivial knot? It's just a knot that's equivalent to just a plain unknotted or untangled circle. So this is sort of what I mean by can you untangle a knot is just it's equivalent to a circle. So you can continuously deform it. And then of course, naturally, a non-trivial knot is just something that's not equivalent to a simple planar circle. Okay, so here's the actual sort of formulation of the problem. So so the way sort of computational problems work is you always get you're sort of given some input and there's some task that you have to complete. And in this case, your input is just some arbitrary knot, and the task that you have to complete is to answer this yes/no question: is K the unknot? So can you untangle it? And so I mean, I say this is a computational problem, but maybe if you've never seen this before, it's like how do you tell a computer how to untangle a knot? It's sort of, I don't know, it's sort of slightly weird thing. Like how do you get a computer to even understand this problem, let alone solve it? So that's sort of the starting point for what I want to talk about. So here's a theorem. So a knot K is the unknot if and only if it bounds an embedded disk. And somehow this is fairly intuitive. Like if something's unknotted, then somehow, I mean, if it does bound a disk, right? If it does bound a disk, then somehow you can kind of shrink the knot following the disk until it gets really, really small. And because the disk is because it's a disk, like once it becomes really small, at some point, like if it becomes small enough, at some point it'll just become a simple planar circle. So clearly, if that disk exists, then you have the unknot. And I mean, I guess the point is it's not so hard to believe this theorem. And somehow, the way or one way to solve this problem algorithmically is to determine algorithmically whether such a disk exists. But maybe this feels like I've replaced one hard problem with another. So what I want to talk about then is how can you get a computer to understand embedded surfaces? So here we go. So firstly, the way you represent sort of three manifolds for a computer is you represent it using a triangulation. So sort of here's a rough definition. So basically, I mean, if you've seen triangulations before or simplicial complexes, the idea is you glue together tetrahedra along triangular faces. So I should mention though that here I'm allowing two faces from the same tetrahedron to be identified. So the triangulations are generalized in the sense that, I mean, it's more general than a simplicial complex, so that it's more general and it's more flexible. So if you've seen triangulations in the context of simplicial complexes, this is more general than that, but it's a very similar idea. Okay, so this is how we represent manifolds, and you can sort of represent surfaces or embedded surfaces using normal surfaces. So these are, well, so I mean, you can read the slides. They meet each tetrahedron in elementary disks of one of these four triangle types, or disks of one of these three quadrilateral. If I just draw an example, so here's like an example of how a normal surface might meet one tetrahedron. And if you sort of have a surface that's in your whole triangulation, then of course it has to meet each tetrahedron in disks of these types. So here's an example of that. By the way, if anyone has questions, feel free to drop me in chat or yeah, okay. Okay, so right, so yeah, so maybe it's still not quite clear how you sort of talk about this sort of stuff with a computer. Like, I mean, the first step, so what we did in the previous slide was we sort of discretize the problem. So you turn manifolds and surfaces into discrete objects, like, you know, triangulations and normal surfaces. But maybe it's still not immediately clear how you sort of tell the computer what this means. So let me talk about sort of how you represent normal surfaces in a computer. So if you have an n tetrahedron triangulation, basically what you do is you count the number of elementary disks of each type in each tetrahedron. So if you have n tetrahedra, there are 7 types of elementary disks in each tetrahedron. So that gives you 7n coordinates, integer coordinates. So basically you package all of these coordinates into a vector, and that gives you a point in R to the 7n, or a vector in R to the 7n. And basically that's, I mean, you just feed that vector into a computer with the appropriate programming so that it knows what that vector means. And that's your representation of a normal surface. So here's a theorem by Harkin. So this is from the 60s. So depending on your perspective, that's either new, very new, or very old. Right, so basically there's sort of 3 fairly obvious necessary conditions for a vector for an integer vector in R to the 7n to represent a normal surface. And it turns out if you take these 3 necessary conditions together, they're also sufficient. So here are the conditions. The first one is super obvious. The non-negativity condition. Because you're counting disks, of course your coordinates have to be non-negative. The second condition, the elementary disks have to match up across adjacent tetrahedra. So what I mean by that is, so you see these blue sort of curves or lines where the sort of disks meet this triangular face. Then because you've got 2 tetrahedra on each side that are glued along this triangular face, your surface has to sort of, like the disks you have in one tetrahedron, they have to be able to join up with the disks that you have on the other tetrahedron, right? Otherwise, the disks don't match up or sort of glue together to form an actual surface. So you can express all of these as you can express all of these relations as a bunch of linear equations in your coordinates. I don't know. I haven't written out the equations, but it's not so hard to. I mean, I don't know. Maybe I leave it as an exercise to the reader to actually write out the equations. Right. So clearly these are necessary conditions. And finally, the quadrilateral constraints have to be of the same type. So let me explain why this is the case. So here are the three quadrilateral types. So just look at the first picture, right? This quadrilateral somehow, if you were to cut that tetrahedron along that quadrilateral, it cuts it in two pieces. It cuts it in half. And if you look at one of the quadrilaterals of the other type, it has to meet. So like, sure. Let's do it this way. So there's sort of an edge here and an edge here that are sort of separated by the quadrilateral. And if you look at the other two quadrilaterals, they go from one edge to the other. So what that means is, if you have quadrilaterals of different types, you have a self-intersection you must have a self-intersection in your surface. So your surface is no longer embedded. So we don't want that. So we insist that all the quadrilaterals are in a tetrahedron. They all, if you have any quadrilaterals, they all have to be the same type. And the theorem is that these three necessary conditions, again, together, they're sufficient as well. Okay. Okay. So
Alex, sorry to interrupt. Am I supposed to? Yeah, I forgot. I mean, what was the protocol for questions? But is this a hard theorem, or is it a deep result, or is it like clear, more or less?
I think it's sort of. I mean, okay. So if you assume all those conditions hold, it's essentially. Let me go back to the picture of the triangles. So if you go back to the triangles, somehow the idea is the triangles topologically, you can always push them arbitrarily close to the vertices. And so once you do that, then you always sort of have room to place your quadrilaterals. And because the matching conditions hold, you know that everything glues together. And so I guess, yeah, so what you're worried about is embeddedness. And the quadrilateral constraints tell you that you don't have problems with your quadrilaterals, and you won't have problems with your triangles because you can always push them arbitrarily close to the vertices. That's basically the...
Right, yeah, so it sounds like it's fairly clear. I mean, it doesn't seem to be like a super deep, complicated.
It's not super deep, no.
Yeah. Okay,
yeah.
Thanks.
Okay, so here's more normal surface theory, and I have to talk about this because I sort of need it for what I'm going to talk about. So the non-negativity condition, that's clearly a linear inequality, and as I said, the matching equations are linear equations. So I don't know if anyone's sort of seen like somehow the idea is if you have a bunch of linear equations and inequalities, that's basically like in R3, what does a linear inequality give you? It gives you like a plane and like a half space where that thing holds. But of course, in a higher dimension, you just have a sort of hyperplane and a half space that's sort of bounded by that. And so if you want a space that sort of satisfies a whole collection of linear equations, and in particular, in our case, this intersection of half spaces is going to be some polyhedral cone in R to the 7n. So here's a kind of, I don't know, schematic drawing of a polyhedral cone, which is completely misleading because this is three-dimensional, but I'm talking about a much higher dimension. But let's press forward. So somehow the most important information you need to know about this cone is sort of a cross section, because every other point in the cone you can get by scaling a point in your cross section. So here's the projective solution space. You take all the points such that the coordinates sum up to 1, and that's I mean it's your cross section, and sort of, as I said, every other point in the cone is just you get it by scaling a point in the projective solution space. In particular, you get it by doing a rational scaling because you've got integer points. And so what we care about in particular often is vertex normal surfaces. So what that means is when you sort of scale the surface down to the point in the projective solution space, that's actually a vertex of the projective solution space. And somehow the reason these surfaces are the most important is because, I mean, if you think about a polytope, which is like the projective solution space is a polytope, then every point inside the polytope is it's a convex combination or a linear combination of the vertices. Or if you're not familiar with convex combination, it's a weighted average, right? If a point sort of inside the polytope is a weighted average of your vertices. So somehow the vertices capture, in a way, all of the information of the polytope. So we care in particular often about it's often enough to focus only on the vertex normal surfaces. Okay, so with all that background, we come back to unknot recognition. So here's sort of one possible algorithm. So I have to black box something, which is given a knot K, it is possible to construct a triangulation of the manifold obtained by sort of drilling out the knot K. So I guess in more technical terms, it's sort of deleting a small regular neighborhood of the knot, which gives you a thing called the knot complement. And so I claim that you can build a triangulation of this. And a fact which we need also is that if K is the unknot, then this disk that I mentioned before, this will appear. So this is, I think the proof also is not super difficult, but I don't want to get into it. It not only is this guaranteed to exist as an embedded surface, it will in fact exist as a vertex normal surface. And so here's your algorithm, right? I mean, there are finitely many vertices in your polytope, so you just check all of them and see if any of them is the disk that you want. Right, so that's the algorithm. Right, so before I say more about that, because I claim that vertex normal surfaces are important, I think maybe it's worth seeing how important they really are, which is, I guess this is sort of the moral of the story. If you sort of go back through the sort of development of normal surface theory, there are sort of a lot of results where again, you can read the slides. If a manifold contains an interesting embedded surface, then very often such a surface will appear as a vertex normal surface. So let me just sort of quickly flash these for people who know what they are. So incompressible surfaces and essential spheres, which are sort of interesting surfaces, these will appear as vertex normal surfaces under the conditions I've stated. So anyway, so the point is looking for vertex normal surfaces is an interesting thing to do. So then the question is, okay, how computationally expensive is this, right? To sort of find these vertex normal surfaces. So here's sort of the start of the answer to that. So if you have n tetrahedra, then it's known that the number of vertex normal surfaces is possibly an exponential function of n. So there's a lot of them. And that means checking every one of them is an expensive task. Computationally, it's an expensive task, which this is kind of sad, but maybe we can sort of refine this question. So, okay, the naive method of just checking every possible normal vertex normal surface, that's a sort of exponential time thing, but maybe we can do it better. So maybe, you know, the amount of time it takes, it doesn't have to be an exponential function. Maybe it's something much better, like a polynomial function. So, right, so this is some work I did in my honors, was to show that, or to sort of answer this question for two types of surfaces, which I will define. So there is a polynomial time algorithm to detect splitting surfaces, but detecting spanning central surfaces is NP-hard. If you don't know what NP-hard means, basically it means there is almost certainly no polynomial time algorithm. So it's sort of an answer to the above question. How am I going for time? I was gonna sort of sketch the proofs for these, but maybe I don't have time to do this, so I will.
I think you have another 5 or so, 10 minutes.
Sure. Okay, so I'm gonna have to. I was gonna talk about what NP hardness is, but let's skip through this. Yeah, I'm gonna skip through this. Okay, yeah, let's just talk about the surfaces. So what's a spanning central surface? So it's a connected embedded normal surface that meets every tetrahedron in exactly one elementary disk. So either it meets in exactly one triangle or exactly one quadrilateral. So what I've drawn here is what would happen if you cut the tetrahedron along the elementary disk. The reason I've drawn it like this is, like, you see that if I cut along this triangle, it sort of separates this vertex, this blue vertex, from this blue triangle. And similarly, if I cut along this quadrilateral, it separates this blue edge from this other blue edge. So if you think about, like, if you look at the pieces that you sort of cut in this way, what you're left with is basically, what you're left with here is what looks like sort of a neighborhood of the vertex. And here, what looks like sort of a neighborhood of the triangular face. And over here, it looks like a neighborhood of the edge and a neighborhood of the edge. So what does that mean? It means when you cut along a spanning central surface, what you get is a neighborhood of some two-dimensional complex. So somehow it's like a decomposition of your manifold. So this is sort of why spanning central surfaces might be interesting. In particular, if you, so a splitting surface, in particular, if you assume that you only have quadrilaterals, so it's a spanning central surface, but you only have quadrilaterals, then when you cut along this splitting surface, what you get is a regular neighborhood of a graph. So what you get basically is a decomposition into handle bodies, or what some of you might know as a Hayguard splitting. So these surfaces are interesting, right? So I've already said this, Hayguard splitting. These surfaces are interesting, and in fact, they always turn up as a vertex normal surface. Okay, so what was the next slide? Right, I think I can talk through the proof of the first part, which is finding splitting surfaces in polynomial time, and this is super easy. Like basically you just pick some starting tetrahedron, and there's 3 possible quadrilaterals there. And the claim is you just look at each of those 3 quadrilaterals one at a time, and each of them belongs to at most one possible splitting surface. Why is that? Because, like, if you sort of if you start at your initial quadrilateral and you just walk to an adjacent tetrahedron, you have to pick a quadrilateral. Because we're talking about splitting surfaces, you have to pick a quadrilateral in the adjacent tetrahedron. So if I pick this one, then matching equations are not satisfied because they don't match up. Similarly, if I pick this one, they don't match up. And basically, there's only one possible choice to satisfy the matching equations. So what you do is you just walk through, you just keep stepping from one tetrahedron to the next, and you just pick the quadrilaterals that would be forced by the matching equations. And if you walk through, either you pick all your quadrilaterals and everything works out, everything matches up and you get a splitting surface, in which case your answer to the problem, does the triangulation contain a splitting surface, is yes. Or you walk through and you find that at some point your forced choices break something. And then you know that, okay, there's no splitting surface that meets tetrahedron delta naught in that initial quadrilateral that you picked. And so you just check each of the 3 initial choices. And if either one of them gives you a splitting surface or none of them do, and either way you get the answer. And I promise that this is something you can do in polynomial time. I mean, it's a breadth first search. So if you know what that is, then you'll know that that's something you can do in polynomial time. So notice, I mean, the point here is that, I mean, you can solve this problem just by searching for vertex normal surfaces, right? Which is an exponential time thing. But using an alternative technique, you can do it in polynomial time. So the point is, sometimes for some types of surfaces, maybe you can use an alternative technique to do it in polynomial time. But for other surfaces, maybe not. And so the claim from sort of the where are we? The claim here is that, okay, so splitting surfaces you can find in polynomial time, but spanning central surfaces, even though they seem like quite similar concepts, they're much harder to find. They're much harder to find. And in fact, you can prove that it's NP-hard, which basically means that unless P equals NP, so unless Millennium Prize problem breaks, then there's no polynomial time algorithm for finding spanning central surfaces. Okay, so I think, yeah, so I wanted to walk through the proof of the Hamby hardness thing, but probably I've run out of time. So I think I'd better stop there.
Thanks, Alex.
But you have a copy of the slides, so you can sort of flick through those if you're interested. There is also, if you're really, really curious about the details, then you can look them up on the archive as well.
Are there any questions for Alex?
Could you mention briefly the idea of the proof?
How
to prove that it's NP-hard?
I mean, the way you show that something is NP-hard is typically is you start with some other problem that you know is NP-hard, and then you show that the problem that you're trying to prove is NP-hard. One way to say it is, if you want to prove a problem A that you already know is NP-hard, and because it can simulate this hard problem, it must be hard itself. And so, sure, I mean, I have slides, so I can very vaguely. So it turns out that detecting Hamiltonian cycles in a graph, in a 3 regular graph, is NP-hard. So the idea is you simulate this hard problem using this spanning central surface problem. So let me just put up the picture. Basically, you can construct a triangulation that you use to simulate a vertex. So if you think about how a Hamiltonian cycle passes through a graph, a 3 regular graph, because it has to sort of it has to enter and exit every vertex. So the cycle has to it has to use 2 of the edges, and it has to leave the 3rd edge untouched. And that's basically what each of these surfaces does. So you've got this surface here that kind of cuts through and meets sort of 2 of these squares. So topologically, because the top of the square is identified to the bottom, topologically, each of these squares is an annulus. So basically, each of these squares simulates one of the edges coming out of a vertex. And this surface basically tells you how your Hamiltonian cycle is passing through the vertex. So there's some details to deal with because there's this extra normal surface, spanning central surface that you don't want, which doesn't represent anything to do with Hamiltonian cycles. But basically the trick is you glue everything together in a way that kind of means that this surface breaks the matching equations. I mean, it's just a trick of it. So I don't know that there's a huge amount of insight to the proof. It's more just a nice proof in the sense that you can kind of see how the triangulation simulates Hamiltonian cycles in a graph, and it's sort of kind of cute.
So you build a specific triangulation for which, I mean, detecting this spanning surfaces is equivalent to the Hamiltonian cycle.
Yes,
probably,
yes.
Right? For
yes,
one
yeah.
specific triangulation, and that's enough, of course, because
yes, because if you could, I mean, because if you could solve this problem in polynomial time, then you could solve Hamiltonian cycle in polynomial time because you just simulate it in this problem. So that means because Hamiltonian cycle is unlikely to have a polynomial time algorithm, you should believe that this is also unlikely to have a polynomial time algorithm, because you can do that simulation. That's not answering your question. Yeah. So yeah, for any particular graph that you could give me, I build a corresponding triangulation such that detecting the surface is equivalent to detecting the Hamiltonian cycle in the graph. And so that means if I wanted to solve Hamiltonian cycle, one way to do it would be to simulate it in this way, using this triangulation and solving spanning central surface. Because our best algorithm for spanning central surface is exponential time, it's a silly way to do Hamiltonian cycle, but it's a way to do it. Does that answer the question?
Yes, of course.
Yeah. Are there more questions?
Maybe we can stop it there for the moment and thank Alex again. Thanks, Alex. So I'll stop the recording.